Okay, so let's just here's one that's for the assignment that's due tonight. So let's talk. It seems like this one has a little bit lower success, so let's talk about this one. So if we've got two planes, let's see if I can draw this here. And say well, that's the best and the worst set of intersecting planes I've drawn today. All right, so how would we find, so the angle between the planes would be the acute angle. So there's two angles between the planes. And so conventionally, when you just say the angle between the planes, you're talking about the acute angle. So this is the one we want. Okay, so how can we find that angle? We find that angle between those two planes. So this has to do with what? Orientation, inclination. So what do we have about those planes relative to orientation and inclination? Yes, sir?
We could find the data between the normal vectors.
All right, so the normal vectors of the planes are what? Lock down angle, inclination, right? So let's do orange shows up. So the second one that I drew, its normal vector is like this, right? And the first one that I drew, its normal vector is like this. Agree with that? So do you see that then the angle between those, it's just like, because those are both orthogonal to those planes, it's just like those two vectors are like the same angle as the plane rotated 90 degrees. Do you see that? So take this one, rotate it 90 to get that. Take this one, rotate it 90 to get that. So that will be the same angle. Do you see that? And so now it's just a matter of, do you know how to find the angle between two vectors? And you should. We've done that before. So if you don't remember, you just got to review that. So, so finding the angle between the planes is the same as finding the angle between the two normal vectors, which define those planes. Okay. So this homework is due at 7 o'clock tonight. And then you have one more due, I think, at 7 tomorrow. And that covers the material for the exam. So what we covered today, and then we'll not get through it, but so I talked about a short video to get through it. The video that I have is actually for the material after today. So between today and the test, you're watching a short video that's important for the test. Okay? But I think, I don't think there's super hard questions about it, but there are questions on the test pertaining to the supplementary video that we'll have after today's lecture. Okay? So, and then you're handing in written homework tomorrow and recitation. Is that right? We're working on that? Okay. Yeah, so you got two more web work tonight, web work tomorrow night, and then tomorrow's written recitation homework. And then that's all, since the beginning of the semester, all material on the exam. And I'll post, I think there's, I don't know if I have review materials for this one or not. It's pretty straightforward. It's everything we've done so far. So web work problems are good. The video lectures, all those things I emphasize. So there's nothing on the test that doesn't pertain to stuff I emphasized in class. So review the videos, take new notes on the videos, rework the web work. And you need to know it more than just how to do basic problems and get answers. You got to understand stuff. So that's really what this is going to be about, is do you understand some more subtleties and nuances that really show me that you get vectors and you get all the stuff that we're doing. So study for meaning and understanding. Don't study for procedures and answers, okay? Because that'll only take you so far. That being said, there are some problems on the test where you have to know how to do it and how to get the right answer. So that's important. But there's lots of also other questions also that are testing to see if you get it. All right? Other questions or any questions? All right, so let's do the last part of this unit here, which is so we're going to talk about equations of x, y, and z today. Equations of x, y, and z, and we've seen two different instances of equations of x, y, and z. Two different examples. Can you think of what those are? Yeah, you got one?
There's like the equation for
A plane. Is a plane an equation of x, y, and z? Yep. And then we've seen something else that was an equation with x, y, and z in it, besides planes. Remember what that was? Is it Winston? Yeah.
equation of vector as well.
Nope. Yeah.
A line.
A line is not. So what I mean by an equation of x, y, and z, what I mean is without any vectors, right? So just a single equation that brings together x, y, and z. So a line would not be that. Remember what else we had? Someone said spheres, right? Spheres. Okay, so we had spheres, and we had planes. So so I was going to write down the standard equations there. So I'll do that fast. So spheres, what's the standard equation? Right? X minus a squared, 1 minus b squared, z minus c squared equals r squared. A, b, and c was the center. R is the radius. Plane. ax plus by plus cz equals d. Or we had the point vector approach, a times x minus x naught, etc. What's ABC in this? Is it the center of the plane, ABC? That's orthogonal vector, right? The normal vector. The normal vector is the plane. Okay, so looking at these are both equations of x, y, and z, and they both form something similar in R3. So what's the commonality here to a sphere and a plane, which are both equations of x, y, and z? What do they form in R3? What kind of thing? Surface, right? So as opposed to like a string of points. A line was like a string of points, kind of a one-dimensional object. Even though it was in R3, it was one-dimensional. You can only go one way or the other. But a surface is kind of like a two-dimensional object. And when you have equations of x, y, and z, those will form surfaces. So we're going to talk about more of these today. So today we're kind of departing. We're going to take a break from vectors for a moment and talk about surfaces in space. More versions or more different types of surfaces. So the first one is ellipsoids. So if I start with the equation of a sphere, and I'm going to take that equation, I'm going to divide both sides by r squared. There's another way to write the sphere. Those are equivalent, right? But now what if I took and I had a different radius on each axis? So instead of the same r squared in each denominator, I let those change. Then it's like in each of those x, y, and z directions, I'm allowing for a different radius. So it looks like this. So there's an rx squared, an ry squared, and an rz squared. And so what will that do? You started with a sphere and you changed the radius in different directions. Then what will you get? Yeah, like so it'll like smush it or stretch it in different directions. So you get like a rugby ball or a UFO or a pill, things like that. And these are called ellipsoids, right? So a sphere is a special case of an ellipsoid where all the radii are the same. The radius is the same everywhere, right? But if you allow for different radii and different axes, then you're smushing and stretching the sphere in different ways. Okay, so this is an ellipsoid. Can we sketch it? Can we sketch this ellipsoid? So what's the radius in the x direction? According to the general equation of ellipsoid, and given this one, what is the radius in the x direction? Some people are saying 1/2. Agree with that? Because it'd be x minus 3 divided by 1/4, and that would be our r squared. So then the radius would be in the x direction 1/2. And what's the radius in the y direction? 3. And in the z direction? 1. Not 0. 1. So let's sketch this. And then what about the... So, and then where's the center of this thing? 3, 0, 2. That's the center. And then what do we say in the x direction? We're going to go how far? 1/2, right? Do that. And in the y direction, I'm going to go 3. 1, 2, 3, maybe like this. 2, 3, like this. And the z direction? 1. So I'm drawing the kind of the key points here to this thing. So it's going to be like a pill standing up on its edge. Do you see that? I'll do my best, but these are not easy to draw by hand. Okay. This. Oops. That. And then something like that. So it's squashed in the x direction, stretched in the y direction. So it's a sphere centered at 3, 0, 2, squashed in the x direction, stretched in the y direction. And that's the center. The center is 3, 0, 2. So ellipsoids, any questions? Make sense? So we got planes, spheres, and ellipsoids. Okay, so other things, we're going to sketch and identify with something called traces. Traces is where you choose a, I think I've it down here. By setting x, y, or z to different constants, the remaining equations of two variables create curves in space called traces. And lots of those traces will form kind of a skeletal structure of the surface. Okay, don't write that down word for word. Just get the idea. Okay? So in order to draw these traces, we have to have a mastery of the basic curves in R2, because that's what you get. So you're going to pick a variable and set it to a constant in your equation, and then you're going to have an equation of the other two variables, and you have to know how to sketch those R2 curves. Okay? So here's kind of an overview of those. So parabolas. So parabolas have this form. So I'm using u and v to be any two of the three variables x, y, and z. So u and v could be x and y and z, or x and z. So this is a parabola. U minus a equals k times v minus b squared. Parabolas have one linear, an equation where one of your variables is linear and the other is quadratic. So that's a parabola. Circles look like this. Just like a sphere, but it's in 2 dimensions, right? So there's only the two variables, either x and y and z, or x and z. Ellipses, just like we talked about. So like an ellipsoid, but in R2. Again, it's a squashed or a stretched circle. Hyperbolas, although we won't do much of this, but hyperbolas are like ellipses but with a minus instead of a plus, but we won't see many of those. But just be aware, that's what you get with an equation like that. And then finally, lines are a linear relationship of x, one of the two variables. So again, u and v could be any of the two of x, y, and z. Those are anything's fair game. And so if u and v are y and z, then you're sketching a curve in the y-z plane, just the way you did in the xy plane. Okay, so what is the role of the a and the b here? So you have u minus a and b minus b. So what does that do to the curve, just as in general for any of those?
Shifts it in some sort of direction.
Right, it's going to be a shift, right? These are going to be a translation, and so is that a units in the positive u direction or in the negative u direction? In the positive u direction, right? And this will be b units in the positive v direction. So it's a translation. A units in the positive u direction, b units in the positive v direction. Okay, so we're gonna look at an equation of x, y, and z, and then we're gonna apply this idea that we're gonna set one of the variables to constants, and then sketch. Right? Then we're gonna sketch curves, which are called traces in space. And when you get a bunch of these traces, then you have a really good idea of what your surface is like. Okay, so we're ready for an example? We good on this? So here we go. All right, so we want to look at this right here. Z equals x squared plus y squared. So it's an equation of x, y, and z. So how will it graph in space? What will it graph as in space? Just in general? Surface, right? So we want to figure out by creating traces, like I just talked about. We want to create traces in space so that if we get enough of them, we can imagine what that surface is like. Okay, so we're going to start with traces by letting x values be constant. So let x equal, say, -3, -2, -1, 0, up to 3, okay? So let's just take all the integers from -3 to 3, or something like that. Let's see, is that what I did? I did. Yeah. And what will we get for any of those? So for instance, when x is 0, what do I get? Which one? Z equals y squared. So now we're talking about graphing in the xy plane, or zy plane, right? So we're going to put y here and z here, because I'm setting x to be constants. And when x is 0, I get z equals y squared. So what does that look like? So like that, right? So this is for x equals 0. So then, thinking about it in R3, so what does x equals 0 mean in R3? X equals 0 is the plane, it's like the plane of the screen, right? So when you're in the plane of the screen, the surface is going to create that curve in the plane x equals 0. So like this. Is that right? Is that in the right place? Why didn't that work? Oh. Doesn't matter. Oh, up here. Sorry. There we go. Here. Okay, there we go. All right, so by saying x equals 0, we're talking about the plane x equals 0, right? And so then the trace that you get is going to be in that plane, and that's this equation that we have for z equals y squared. It's going to be in the plane x equals 0. All right, so what about x equals negative 2? What will we get for that? She wants z equals 4 plus y squared. Agree with that? Blue here. So when x equals negative 2, we'll get z equals y squared plus 4. So what does it mean? It means that in the plane of z equals negative 2, can you imagine that? We'll have the curve of y squared plus 4. So what is this curve of y squared plus 4? Like that, right? And where will that live in the surface? At x equals negative 2, right? So here's the plane x equals negative 2. And so for the plane x equals negative 2, the trace of the surface will be this parabola y squared plus 4. What about positive 3? Will be the last one we do. It's not equals. Z equals y squared plus 9. So y squared plus 9 will live in what plane? X equals 3, right? So here's the plane x equals 3, and then we're going to have that parabola y squared plus 9. So if we just kept doing that over and over again, we'd get a bunch of these traces, and they'd all be parabolas. And what could we say about those parabolas? Since we're doing x squared, no matter what x value we pick, that x squared will always be what? Positive. So therefore the z will be a positive value plus y squared. And so all these parabolas will live above the xy plane for positive z. We'll get something like that. So here's a bunch of those traces for constant x values. 3 of which we found, right? X equals 0, x equals negative 2, and x equals positive 3. So even with just those traces for constant x values, you start to get a picture of what the surface is going to be like. Okay, so I'm going to take a 10. So what I want you to do is I want you to do traces for constant z values. So you're going to pick different z values around 0, pick some negatives, pick some positives, pick 0. And then sketch those traces, and that will be, when z equals 0, you'll be sketching the xy plane. So do z equals, do negative 2, negative 1, 0, 1, 2, and 4. You can skip 3. So for those z values, I want you to find the equation of the trace, sketch the trace, and imagine, or try to sketch it in R3, just the traces, okay? And if you're not sure, if you need help, ask someone around you, okay? Did you get, what happened when you plugged z values in constant z values? What kind of things did you get?
For most of them, I got circles, but for the negative ones, I got
Okay, good. So when you say most, then what gave you circles?
0, 1, 2, 4.
Okay, so for the positive z values, did you get circles? And then for negative values, what'd you get? Doesn't exist. Therefore, what do we know? What does that tell us? Yeah, there's going to be just the graph won't live there, right? The graph won't live there. Okay, so let's take a look. So when c is And that's the one you didn't do. So when C is 4, what do you get? Did you get a circle with radius 2? Yeah, and so where does that circle live? So how would you relate that circle to the surface? Where does it live? What's that? At height z equals 4. Right? Yeah, because that's how we got the circle. We got the circle by saying z was equal to 4. So now we're only talking about z equals 4, that plane. So there's the plane z equals 4, and there's the circle x squared plus y squared equals 4. All right, and so then when the z value increases, what happens? Circle gets bigger, right? So here's z equals 5, has a radius of square root of 5. Z equals 6, square root of 6. There's z equals 7. And then z equals 0 gives what? What does z equals 0 give? Just the point, the origin. Just that point. And then when z is negative, you got nothing, right? You got nothing. So if we put all those together, it looks something like that. So here's these are the traces that you get for constant z values. Okay? I can also do the traces for constant y values. We didn't do that, but here's what those look like. Just like the ones for constant x values, but in y planes, right? Constant y planes. So there's traces for y values. Then you got our traces for x values. Those are the first ones we did. And then the traces for z values, constant z values. So we're making like a net, right? You make a net, you got lots and lots, and now we see exactly what this thing is going to be like. Right? It's like the tip of a rocket crashing into the ground, right? And so, but this is only the traces. Then we imagine the surface, right? The surface would be all points that these traces live in, right? All points these traces live in. Something like this. Okay, so does the idea of traces make sense? Setting one of the variables to constant values and looking at in that plane in R3, you're going to get a curve that you get when you set that variable equal to a constant. That curve lives in that plane, and all those curves put together gives you a surface. That's the idea of traces. So this particular kind of surface is called a paraboloid, right? So it looks like a three-dimensional parabola. It's parabolic in x and z and y and z, and then the horizontal cross sections are the circles, circular cross section. So this is called a circular paraboloid. It's a circular paraboloid. Any questions on this example? Okay, so let's summarize paraboloids here and look at some different variations. So paraboloids. This is kind of our basic paraboloid. This is like our reference paraboloid, just like y equals x squared was our reference parabola, right? Like all others, so like y equals x squared is like our baseline. Same with paraboloids. This is our baseline paraboloid. Setting x or y equal to various constant resulted in traces that were parabolas, like those vertical parabolas, right? And setting z equal to constants resulted in what? Again? Circles, right? When you set z to various constants, those traces are also called level curves. Okay? Why? Because a constant z means you're at a constant level, right? So that's when you hear level curves, what you're talking about, you see that in the Weber? Level curves are referring to traces for constant z values. They don't have to be circles. They were circles for the paraboloid that we did, but they can be anything. Level curves can be anything depending on the equation that you have. Okay, so what can we do to get various paraboloids? There's three things we can do. We can change the orientation. We can have, say, y equals x squared plus z squared, or x equals y squared plus z squared. That's the first thing we can do. So that changes kind of the direction that it opens, right? Does it open on the, how does this open? How did our paraboloid open? Positive z direction, right? It opened up in a positive z direction. So if you wanted one that opened in the positive y direction, it would be y equals x squared plus z squared, right? So that's the first way we can adjust this. The next way we can adjust this is we can translate it. We can just move it. And what in the equation shows us that we've moved it, translated it. Remember, yes, we said like x minus, so translation. U minus A, V minus B, W minus C. Remember? So if U, V, and W are some combination of X, Y, and Z, this is what translates, right? This is what translates. And then the last thing is stretching or smushing it out of a circle, right? The one we had was circular. We had all circles for our level curves. So just like with ellipsoids, you do the same thing. You kind of change the radius in that particular direction by dividing by r squared. Okay, so I want you to try to sketch each of these paraboloids that have all the different variations going on, right? It could be opening on a different axes, it could be translated around, and it could be stretched and smushed. See if you can sketch these five. Take 5 minutes and see if you can sketch them. Okay, this next one is our standard one. How is it stretched and smushed? So in the x direction, what about, so if we had our, does that show up? Does that show up? Can you see that? Yeah. So there's our y equals x squared, z equals x squared plus y squared. So then in the x direction, stretched out or closer in? Stretched out, right? And then in the y direction? Closer in, right? So like this. So that you get what your cross sections are ellipses like this that are longer in the x direction. Now that's the best paraboloid I've drawn all day. All right, so it's stretched in the x direction and smushed in the y direction. So that if you took cross sections, you get ellipses that are all proportional to that, right? Like at a 3 to 1/2 to 3 ratio, right? So your radii would be in a 1/2 to 3 ratio, every single one as they got bigger, because it's opening up, right? It's opening up.
So along the x it gets bigger?
Along the x, it's like actually 6 times, the radius is 6 times as much along the x as it is in y, right? Because it's 3 to 1/2 ratio. But then those ellipses are getting bigger as you go up the z, right? Because it's opening up. So for any given ellipse, the ratio of z to y is always 6. Z to x to y. X radius to y radius is always 6. 3 to 1/2. Okay, this is opens in which direction? Opens in the positive x, opens out at you, right? And as center, where's the center to that one? 1, -2, 4. So the center's at 1, the vertex, 1, -2, 4. It's going to be circular or elliptical? Circular, right? Elliptical ones are the ones that you divide out by the radius squared, right? So this will be circular at 1, -2, 4, and it open in the positive x direction. Last one, center, what's the vertex of that one? -1, -3, 2 will be the vertex. -1, -3, 2. It will open in what direction? To the right. It'll open to the right. Okay, and it'll be stretched, right? 4 times in the x direction. So it'll be stretched a little bit more vertically than horizontally, right? Stretched to a radius of a ratio of 5 to 4, z to x. All your ellipses coming this way will have a ratio of 5 to 4 radii, z to x. Does that make sense? Okay, what about, so the next one we could talk about then, a different kind of equation is this. Z squared equals x squared plus y squared. So will that be a paraboloid, first of all? No, because it doesn't have this form. Paraboloids have a linear term equal the sum of quadratic terms. That's what all these did, right? Linear term equals sum of quadratic terms. This is not that. This is a quadratic term equal to the sum of quadratics. So it's going to be something different. So what about the z? What about the level curves or the z traces? What will you get for those? Circles. Same circles you got for paraboloid? So what's different about this? Right. So your z now becomes what for the circles? Now your z value is actually the radius. So then how does that change the surface? If your z value is actually the radius, yeah, so radius is increasing linearly with z, right? If z and the radius are the same, you got z, so we're doing what? Z, it's up there. Yeah, z squared equals x squared plus y squared. Then your z is your radius. So as you increase in z, your radius increases with it. So you get a linear increase of radius with z. And so how will that shape be different than a paraboloid? And then what about negative z values? Do they work? You get those same circles again for negative z values because they get squared. So this one does live below the z-axis. So what do we get? Here's a bunch of those level curves. So this is a double cone, right? So it's like a paraboloid in that your z traces or your level curves are circles, but now they increase linearly. The radius increases linear, so you get straight sides, not paraboloids anymore. And you get the one below too, because your negative z values still give you a valid circle. So this is called a double cone. All right, with double cones, you have all the same variations as with paraboloids. I can change the direction that it opens by changing the variables around. I can translate it by taking x minus, y minus, z minus, moves the vertex and moves the whole double cone. And we can have elliptical double cones by smushing the so this is an actual circular. So this one's circular. You could have elliptical. By dividing by different r squareds, right? Again, you can translate it, or you can have it open in different directions. So what if I were to take the square root of both sides here? What would I get? Z equals Square root of? Is that what I would get? Plus or minus. So what does the plus or minus have to do with anything here? So the plus is for positive z's. So what is that? The single cone that's above the xy plane, right? And then the negative is? So that's going to be a positive number. Take the opposite of it. So this here is for the bottom cone, and this one here is for the top cone. So you write it as z squared equals x squared plus y squared. You get both. Take the square root, you get the plus or minus, and that separates it into the two different cones. Sometimes they'll give you, sometimes you'll just be given this, right? And you have to recognize, oh, that's the top half or the single cone from a double cone, z squared equals x squared plus y squared. And this kind of thing you can have with any of the equations. It doesn't have to be just cones, right? Anything that's dealing with as quadratic terms, you can solve for one and take the square root of both sides, and you have the same kind of effect. So it's not just double cones that you might see there, something like this. Any questions? So, 5 things on your plate. Just 5 things. Let's list them. Web work Wednesday. Web work Thursday. This is all, and all this stuff is great for studying for the test. Written homework for recitation. Oh, and recitation, then you'll be a study session for the exam. Okay. I'll give him some practice problems for you guys. All right. What else? 4 is watch the video. And this will all be on Blackboard. Number 5 is study more.